Hot Globe here with Dr. Ralph Keeling, curator of the Keeling Curve at the Scripps Institution of Oceanography in sunny La Jolla, California. And very briefly, Ralph, what is the Keeling Curve and why has it been called one of the most significant scientific projects or discoveries of the 20th century and the 21st century too?
Well, thanks, Steve. Of course, I'm happy to be here. So the Keeling Curve is a record of rising carbon dioxide in the atmosphere. It was started in 1958 by my father, Dave Keeling, and it's the location is significant because it's in the middle of the Pacific Ocean, way up on the volcano. It's very remote from forests and cities, and it produces a very pristine record of changes in atmospheric carbon dioxide. It's showing a rise over time, but it also has a seasonal cycle, which is showing the breathing of the Earth. It's a kind of a nice indication that we live on a planet with life. But it also, very quickly, even in the first few years, showed a buildup of CO2, and it was the first really good evidence that humans were having an impact on the global atmosphere in a way that could affect global climate. And to this day, it remains kind of an inspiration for people. Look at this curve and say, wow, something big is happening. I at least have to know about this. And many people looked at this curve and decided it was inspiration for them to move into this field. So there are scientists who, modeling climate impacts of CO2, looked at this curve and said, wow, this is a big issue. This is something we ought to be studying. And I guess the record is incredibly detailed, so it's a kind of a beautiful achievement of science and showing so much detail and so much information. But it's also super valuable. I mean, it's a kind of a bottom line for where we are. If we're going to bend the curve, what's the curve? Well, this is the curve. This is the curve we need to bend.
Right.
And it also, because it's so long, it's also a great record for assessing whether we're on track or whether we're not on track and whether anything surprising has happened, because we have now more than 65 years of data establishing what natural variability in this rise looks like. We can make forecasts going forward based on this curve better than we could without it.
Is there any, is this magnificent measurement apparatus in any danger from the current administration?
Well, there's certainly threats on the horizon, and so how real they are is hard to say at this point. There was a issue involving the Hilo office of the Mauna Loa Observatory having its lease not renewed. That's a kind of minor issue. If the funding were still there, they could move to another office. So that got a lot of press attention. It doesn't necessarily pose an existential threat if nothing else went on, because one could work around it. It's important to point out that the observatory is run by my colleagues at the National Oceanographic and Atmospheric Administration. So the operational details are maintained by them. We here at the Scripps Institution of Oceanography collaborate with them to get measurements.
With NOAA.
With NOAA, yeah. And so some of the work that's done through NOAA is contracted to universities through various cooperative institutes. That funding could be threatened by the need to get approval at a political level. We saw an example of that last week with grants to Princeton University and the Geophysical Fluid Dynamics Lab collaborative there that got basically denied. Presumably because they have some dimension that has to do with climate. So some of the work we do here at Scripps comes through a similar collaborative institute. I should point out that in addition to measuring carbon dioxide in my group, we also measure changes in atmospheric oxygen. Turns out oxygen is decreasing in the atmosphere as CO2 is going up. What does that sound like? Well, it sounds like what happens when you have a fire, right? It takes up CO2, it takes up oxygen from the air and makes CO2. Well, guess what? We got fires burning fossil fuels in all our gasoline engines and power plants. So the decreasing oxygen is just a reflection of the same thing that's causing CO2 buildup, but it provides additional diagnostic information.
Right. So Explain why fossil fuels, from your point of view and from your measurements, are really the overarching cause of what's going on with the curve, with increasing CO2.
Well, it's pretty simple. And some people say, how do you know the buildup is caused by fossil fuel burning, not caused by something else? I should point out that historically that question was never really viewed as needing even to be answered, because it was there was another question came to mind immediately when my father had these first measurements, and that is you could see how fast it was building up,
Right.
and you could do the math on how fast you expected it to be building up based on the rates that humans were using and burning fossil fuel. And what you found was that the buildup was slower than the amount we were adding to the atmosphere. So it proved that carbon dioxide was going elsewhere. So the question was always, where is this carbon dioxide that's not building up into the atmosphere going to? So the answer, it's more than enough CO2 being emitted from fossil fuel to account for it. You could make an analogy. So let's suppose you have a chicken coop,
Right.
and on day one, you put 10 chickens in it. And then you come back on day two, and there are 5 chickens in it. What's the question?
That's going to hurt the egg price issue, but that's another diver.
But what's the question? The question is, what happened to the 5 chickens that disappeared? Right? So that was always the question with CO2. What's happening to the CO2 that's not ending up in the atmosphere?
Not that we were increasing it, but where was it going? And I might possibly the ocean, possibly the land. What do you think?
Yeah, exactly, exactly. That was the issue. So, and of course, you could say that this fingerprint with CO2 going up and oxygen going down is also consistent with it being fossil fuel burning. There's isotopic changes that are also consistent with that. But the overwhelming simple reason that we don't worry about that is because we know how much fossil fuel we're burning, and we're burning a lot. We're dumping CO2 in the atmosphere in massive amounts, and it's not all staying there. Some of it's spreading elsewhere. That's what's going on.
Okay. And people talk about 1.5, C, and please translate that into Fahrenheit, or 2 C. Are we blowing past that? How dangerous is the situation right now?
Well, you're asking me to do the math on what 1.5 C is, but it's probably 2.5 or so, or 2 point something degrees Fahrenheit. These numbers came about from the application of the science to try to inform how to stay within dangerous limits for the Earth. So this goes back to the Framework Convention, with the goal of avoiding dangerous interference in the climate system. What is dangerous? Well, one measure of danger was that you don't go above some temperature threshold. And they originally set a threshold of 2 degrees C, that's where it got dangerous. And then people realized, oh, that's a little bit deep into climate change. There are particularly countries like the low-lying Pacific Island states that were going to completely flood it out in a 2 degree C world. So they didn't like that. Why aren't we trying for something a little more ambitious? So then they moved the target to aspirationally also be 1.5. Problem is, we're basically already at 1.5. And we're blowing right past it. And CO2 is rising faster than ever in the atmosphere. It's not just at the highest levels. It's rising faster than ever. Temperatures seem to be rising faster than ever. So it's really hard to imagine that we're going to put on the brakes fast enough to even stop by 2 degrees C. Not that we shouldn't try, but it's going to be a pretty hard target to hit, given all the investment we have already in fossil fuel related infrastructure in our society that fuels our power sector and our transportation sector and so forth. So it's going to be very hard to move to renewals fast enough. Again, not that we shouldn't try.
Right.
But I think more realistically, we're heading towards about 3 degrees C now.
3 degrees. What does that mean in Fahrenheit, and what would that mean in terms of fires, drought, floods, and all the rest of the 4 horsewomen of the apocalypse?
Okay, let's see. So 9/5 of 3 is 27 divided by 5. So that's about a little over 5 degrees C if I did the math right.
I should say that
5 degrees Fahrenheit.
I should say that you did get your PhD at Harvard, and we both went to Yale. But
Well, you're asking me to do math in my head. I hope I did it right.
You did. All right, go ahead.
Okay,
Sorry about
okay.
that.
So yeah, I mean it's hard to put these out even whether it's 5 or 3 degrees C or Fahrenheit or Celsius. It's still a little abstract, but
Yeah.
these are huge changes in climate and that affect all sorts of aspects of the world around us and what's safe and what's not safe and where to live and so I mean the last ice, to put it in perspective, the last ice age, when
Yeah.
we had massive ice sheets over the planet, the world was about 5 degrees C colder. So 3 degrees C warmer is almost an ice age equivalent temperature change, but going in the other direction.
Wow.
So you can expect that in a 3 degree C world, eventually the major ice sheets are going to massively melt. Sea level is going to go up eventually, probably tens of meters. That's like 30 feet or so or more. It won't happen overnight. It might take 1,000 years for that to happen. But we've set in place massive changes that are unstoppable,
Unstoppable.
pretty much, unless you massively geoengineer the planet to somehow preserve life. We need to build a refrigerator over the poles to keep the. I don't know how that's going to work.
But let's say we're talking 2050 or at the end of the century. Is there any modeling or your own opinion about where we're going there?
Well, I'm not in the details of the modeling. I'm a carbon person, so you're asking me a little outside of my specialty here. But I mean, one way to think about this is think about risks today.
Okay, risks today.
I mean, let's suppose you live in a place that's prone to wildfires. How do you know how bad even a wildfire in the next couple of years could be? What's the basis for assessing that? Well, we don't have a history going back decades and decades to know what a 50-year fire looks like because we're not living in the climate 50 years ago.
Okay.
So in order to assess fire risk today or flood risk or any risk, you need a model to tell you how far we've moved off normal so you can predict extreme events like we've never had before. So we're already living in a world that's heavily changed, and you can see it in what's happening to insurance rates because the insurance companies can't just afford to assume the risks are the same as the past. They have to make inferences about new levels of risk. I think I had a knock on the door.
I did. That was a knock on the door here at Scripps Oceanography. Who could it be? Is it Doge? I hope not. What does NOAA do that's so important for America, for Americans, and for humanity?
Well, I mean, NOAA does a number of things, and of course, they run the weather forecasts.
Weather
The
forecasts are
National
important
Weather
to everybody. Go
National
ahead.
Weather Service. They also do things like looking after fisheries and some other related things like that. But they also have a research division called the Office of the Ocean and Atmospheric Research. And this is basically fueling research to improve all aspects of weather forecasting and other things. So it's the research arm, but the research arm is also doing quite an important suite of long-term observations of the oceans and the atmosphere and so forth that help us understand what's coming in the future. And for example, get back to this fire risk question. How do you know what the fire risks are today? Well, you need a model that's telling you how the climate's responded already to the increases in CO2 in the atmosphere. So you need to understand what's happening with CO2 to even understand today's fire risks. And so the Office of Ocean and Atmospheric Research, one of the things they're doing is they're in partnership with us here at the Scripps Institution of Oceanography. They're measuring the buildup of greenhouse gases and related species in the atmosphere that track changes in the large-scale composition in order to basically ground the understanding of how the system is changing. They're supporting measurements of ocean temperature at the surface and throughout depth. They have observing systems that look at changes in coastal areas that affect everything from fisheries to pollution dispersion and so forth. The society really builds on these resources from NOAA to advance businesses and make assessments of risk and handle emergencies. And a large fraction of this nationally is coming through this OAR office, which is potentially the Office of Ocean and Atmospheric Research at NOAA. So it's a really important part of their enterprise, and one that's now especially at risk.
Especially at risk. I mean, is there any rational reason to put this at risk? Would anybody want to do that for a reason?
Well, I mean, the latest pushback from or what is it called, passback, from the Office of Management and Budget from the White House is has listed OAR as something that should be substantially downsized and probably, and I don't know the exact language, but they were going to divide up some portion of it and put it elsewhere. But the important point is that what this office does is relevant throughout society. Whether you're on one side of the aisle or the other side of the aisle, you need to worry about actual risks to things that you're doing, making investments long term. Insurance companies, businesses, agriculture. What trees do you plant? How much of the forest is going to grow? These are basically economically important sources of information that depend on understanding how the climate's changing.
All right, so it seems like crazy to mess with something that important.
I guess I'd also say that the U.S. really has led in this in the past, and part of what makes our country and has basically underpinned our prosperity and our stature in the world in the last few decades is the U.S. investment in science in general, and our investment in the climate, the science of climate and weather and environmental change puts us also in the forefront of understanding these things. So we have been leaders. We're a magnet for talent, or have been, and that's served us well.
Right. Switching off just a little bit. So fossil fuels are much more important than, say, reforestation. You actually have the figures on where the CO2 is coming from. Talk for just a second about why forests are not necessarily the carbon sink they could be.
Yeah, well, I think it's so this is really on the question of what could one do to bend the CO2 curve so that it doesn't go up more. And the main thing driving it up, overwhelming cause, is fossil fuel burning. And so it's going to be very hard to significantly bend the curve without reducing emissions of fossil fuel CO2. And that means moving over to more efficient technologies and fueling it with renewable, sort of wind and solar. This is something that people have heard a lot, but it bears emphasis that there's so much fossil fuel being burnt, it's going to be hard to move away and reduce the curve without getting off fossil fuels. Now, at the same time, people are talking about enhancing the sinks. Remember I said that not all the CO2 is actually staying in the air, some of it's going elsewhere. Why don't we just increase the sink uptake, and that'll help offset fossil fuel emissions. And so there's talks about various technologies for removing CO2 in the air, which could be viewed as a kind of a sinks enhancement technology project or goal. And among them is growing more forests, or reforestation or afforestation. And those kinds of natural sinks have been much discussed, and they do have a role to play because they do take CO2 out of the air, so don't get me wrong.
Yeah.
On the other hand, it's hard to imagine that they're going to scale up to be more than a small fraction of what we're emitting in fossil fuels. I mean, one way to look at it is that, how much vegetation, if you look at all the carbon in vegetation around the planet, it's trees, including their roots and grasses and shrub. You took all that, and let's suppose you burn it.
Okay.
How would that compare to the amount of fossil fuel we've burned so far?
If you burned all the green, okay.
Yeah. Any idea?
10%?
Well, yeah, it's in that direction. It's more. Well, the point is that we've burnt so much fossil fuel that it's approaching, or maybe probably even surpassing, the scale of all the vegetation on the planet. And the only way vegetation takes carbon out of the atmosphere is by putting carbon as biomass somewhere else.
Uh-huh.
And what I'm saying is that the Earth didn't have, to offset the fossil fuel emissions so far by growing more forest and stuff, you'd have to double the amount of biomass in living biomatter on the Earth. Now, there's more potential in soils. Soils hold a lot of leftover detrital matter, just organic compounds that are bound up with the soil. So there's more potential in soil than there probably is in vegetation, but soils don't normally accumulate carbon very fast. And I should point out, any of these sink processes that have carbon, just hanging out there in the atmosphere, in the climate system, or in the shallow layers of the soil, are subject to disruption. So just because a tree is growing and flourishing today doesn't mean it's going to grow and flourish in the climate of 50 years. So you're not guaranteed to have a secure long-term repository by putting it in a tree. Any tree anywhere is vulnerable to something happening to it, whether it's fire or pests or some kind of massive drought of a sort that the trees never endured in the past. So a better sink, in a way, if you can make the technology go, is to bury the carbon deeper in some reservoir, or intervene in such a way that you're effectively titrating the carbon, reacting in a permanent way, so that it's not part of the atmosphere pool anymore.
Well, how do you stay cheerful? Because these are pretty galling statistics. It's the perspective that you are very close to and understand, in fact, have given the world. Yet, do you go surfing? Do you have kids? You seem to smile a lot.
Well, that's a sort of a philosophical question. I mean, we all know that we're going to pass away at some point. And so you try to live your life to the fullest with the highest purpose you can, and not lose sight of the fact that there's years left to do some good on this planet while we're still here. So that applies also collectively to trying to move the needle on this climate problem. So one way I put it is that, as much as we've come up short in a big way to mitigate the climate problem so far, the buildup of CO2 and so forth, it's still the case that the best time to intervene is now. So I often say there's no punting.
No punting, like
no
in
punting
football.
on the climate. Yeah. So what does it mean to punt in football? Well, it means that you're kicking the ball downfield because you got to the fourth down and you couldn't carry the ball any further from the moment. But the assumption is that you're going to get the ball back and be able to carry it again in the future. But there's no punting on climate. We can't kick this the problem down the road and come back to a point that's equivalent to now. We always have to go for the fourth down every time around.
Okay, we're going to go for the fourth down. I like that. Well, thanks, Ralph.
Okay.
That's fantastic.